Hey everybody, and welcome back. Or if it's your first time here, welcome to this channel. I'm David Townsend. This is the Net Academy, where we are learning networks together. And on this video, what I'm going to go through is more detail into the BGP or Border Gateway Protocol routing protocol. But specifically what I'm going to go through is route reflectors. I'm going to be going through and answering questions such as what is a route reflector? Why is it of benefit? What does it actually do inside an autonomous system? And of course, in Juniper Junos CLI, command line interface, how do you actually configure a MX or QFX, EX, etc. router to be a route reflector? So first things first, we're actually going to go through what is a route reflector, why is it around, and as we know from other sessions and other videos that I've done, and here's a link just to example on iBGP, is that you need full connectivity, you need a full mesh of those routers connected to one another in the same autonomous system, and that has some scalability issues around it, hence route reflectors to the rescue. So we're going to go through why route reflectors actually solve that problem, how they actually break that rule, but also the rules behind route reflectors themselves. And then we're going to go through the lab and actually show you in the lab how to configure this on Juniper Junos. So enough said, so let's just get straight on the lab. So let's get on with the theory of BGP route reflectors. But to really understand why we need route reflectors and why they are of benefit, let's first look at iBGP or Interior Border Gateway Protocol and what is absolutely fundamentally required when you start looking at iBGP peering within the same autonomous system. So I'm just going to draw a few routers. So say here we've got R1. Over here we've got R2. I'm a terrible drawer, so apologies for my lack of artistic skills. Here we've got R3, R4, and let's make it a bit more interesting right at the top. Let's do R5 as well. Now with iBGP, what is required is for all these routers to have iBGP peering to one another, so they have a full mesh of connectivity, and that's important. And if you don't know why, please refer to one of the videos I've done in the past. But if, for example, a network prefix is coming into router R4, so this would be eBGP. Now the rule of iBGP is that R4 is going to advertise this onto router R3. That's fine, that's great, because router R3 knows how to get to router R4. However, the rule of iBGP then states an iBGP peer, router R3, is not then going to forward it on to router R5, who's then not going to forward it on to router R2, who's then not going to forward it on to R1. So as soon as this route hits router R3, R5, R2 and R1 do not learn about that network layer reachability information, i.e. that prefix that has been received on router R4 and advertised to router R3. And the big reason for this is that with iBGP, the loop prevention mechanism is the AS path, or autonomous system path. So if we just say, for example, all of these routers from R1, R2, R3, R4 and R5, let's say they're in ASN 6500, just for example. And let's say this BGP peer has come from 6501. Again, just random number. So as this router comes in, R4 is going to see, within the AS path, which is one of the BGP path attributes, I can see that it has originated from whatever autonomous system, or maybe from autonomous system 65101 itself. But then when it advertises that NLRI, that prefix, onto router R3, R3 will check its AS path to see is ASN 6500 contained within that AS path itself. Now at this point with iBGP, it's not going to be in there because with iBGP, all these routers here from R3, R2 and R1, they do not update the AS path to contain their own ASN. It's only when, for example, if this prefix here was to leave router R1, would that ASN path actually be updated in the update message itself. And it's because of that that router R3 does not then advertise the router onto R5, because R5 has no way of checking is my ASN 6500 within that AS path. So it assumes, and we know the saying around assumptions, it assumes that potentially my own AS number could be within that AS path, and as such it's just not going to accept those packets. It's not even going to build, well, it would build the adjacency, but it's just not going to accept those update messages with that prefix, i.e. that network layer reachability information. And also what is very important is next hop. This is actually one of the first BGP path attributes before it starts looking at local preference and origin and AS path, multi-exit discriminator, etc. And if you don't know what those BGP path attributes are, please just check out this link. It's all explained there on one of the videos I've done. But R5 needs to know what is the next hop to get to this NORI. So it needs to know how to get from router R5 down to router R4. R2 as well needs to learn how am I going to get to router R4. R1, guess what, needs to know how to get to router R4. So you can see this gets quite messy. But absolutely every router needs to know what is the next hop IP address to get to that destination, which is why in the iBGP world we need the next hop self policy attribute or policy option, or some kind of policy which defines if you want to get to this destination, your next hop is through me. So R5 is going to have a next hop policy. R2 is going to have a next hop policy. And where would these next hops actually be defined? These next hop selves, they would be defined on router R1 and on router R4. So that's two things immediately you have to be aware of when it comes to iBGP. i.e. we need a next hop self policy option, a policy that defines if you want to get to these external networks, these external prefixes, whatever they are, you need to go through me, and they are defined typically on those eBGP peers themselves, in this case router R1 and R4. Also those internal BGP peers R2, R5, R3 and R1 again, they have no way of identifying is this path loop free, because iBGP, it doesn't update the AS path as those prefixes are advertised through the network itself. And as such, this comes back to the original point, and the third one I want to highlight is that to have iBGP working, you need a full mesh of connectivity. And by that, what I mean is R1 needs to peer to router R2. It also needs to peer to router R5. It also needs to peer to router R3. It also needs to peer to router R4. But R5 needs to peer to router R3. It also needs to peer to router R2. And it needs to peer to router R4. R3 needs to peer to router R2. It also needs to peer to router R4. I think I've got it all there, but you can see this really becomes a scalability issue. And that's just with 5 routers, and there's actually a calculation, a very simple calculation that anyone can use to calculate how many connections, how many peering adjacencies do you need in an iBGP network. And that calculation is n, in brackets, n minus 1 divided by 2. So I'm just going to do divided there, missed that out. So n is basically the number of routers. So here I've got 5 routers, R1, R2, R3, R4 and R3 and R4. I've mixed them up there, but there's 5 routers in total. So we've got 5 in brackets 5 minus 1 divided by 2. So that's then 5 times 4 divided by 2, 20 divided by 2, and thus we then have 10. So with a network of only 5 iBGP routers, you're going to need 10 connections to have this full mesh connectivity within the iBGP network itself. Now, for 5 routers, that's manageable. But if we then just go up to, say, 10 routers, so say you've got, and I'm just going to draw it down here, so say you've got 10 routers in the network, so 10 in brackets 10 minus 1 divided by 2 again, that's then 10 times 9 divided by 2, that's then 45 connections. You need 45 connections to have a full mesh of connectivity when you've got 10 routers. That's a lot. And as I said, this then gets very, very messy. And because of that AS path and this next hop self, and then this requirement within iBGP to have full mesh connectivity, what can you use? What can you have? What can you deploy to address these scalability issues, to address this next hop self, to address the AS path? That's where route reflectors come into it. So what do route reflectors do? Well, you have to be careful. You have to think about where you want to deploy a route reflector. But let's say, for example, we've got this eBGP peer, again advertising some network layer reachability information, i.e. a prefix or prefixes, which is coming into router R5. Now, using the iBGP rules, R5 is then going to advertise that onto router R4 and up to router R2. But it doesn't go any further from there. So R1 and R5 will not then learn about this network layer reachability information, those external prefixes, whatever they may be. But what if we then configured one of these routers, or maybe even both of them, to be a route reflector? So let's say R2 then becomes a route reflector. What R2 is then going to do, if these are clients, so I'll say R5 and R1 is a client, and that's a big point here, client, the route reflector R2 will then advertise that learned prefix from the update message onto router R5 and down to router R1. Now, whilst that might sound similar, it's not, because R1 does not have an adjacency. It does not have a BGP adjacency built to router R5. It doesn't have the adjacency built to R3 up here. It won't have the adjacency built to router R5 up here. So just by deploying a route reflector, you significantly reduce the amount of iBGP peer connections, adjacencies that you actually need within that autonomous system. The route reflector literally does what it says, i.e. it reflects routes. But there is a rule set that you need to be aware of when it comes to route reflectors. So rule 1, and let's say a client here is router R1, and this is receiving a prefix coming in, or maybe from an iBGP peer. The client will advertise that learned prefix to other clients and also non-clients. If you're wondering what a non-client is, as we know in Junos, what you can do is you can configure groups. And within that group, you basically define a cluster to have a route reflector. And then you define neighbors as well. So all those neighbors that fall within this particular group will be a client. If you then have another group, so let's just call it group B, all those clients, so all those neighbors within group B will be non-clients. But rule number 1 is basically when a client advertises a prefix, it will be advertised to both clients and non-clients. What happens though when a non-client advertises a prefix? So rule number 2, we've got a non-client. Who will that prefix be advertised to? It will be advertised to clients only. So a non-client will not advertise a learned prefix to another non-client. So only clients will advertise prefixes to other clients and non-clients. Non-clients will advertise a learned prefix to clients but not to other non-clients. What happens when you've got eBGP? And this is actually the third rule. If you've got an eBGP peering, it pretty much behaves exactly as it has done. So this prefix is coming in here, and R5 sends it up to router R2, which is a route reflector. That eBGP learned prefix is advertised to both clients and non-clients. So those are the three rules that you need to be aware of. So just in summary, rule 1, when a client within that group where you have that cluster defined, and I'll come on to what cluster is in just a few minutes, but all neighbors within that group, I'm just going to do neighbor here for short, so say this is group A, all neighbors will become clients within that group. And rule 1 defines that client, whoever that client is, will advertise that learned prefix to other clients, but also to other non-clients who reside in a different group, i.e. group B. Rule 2 defines when a non-client is advertising a learned prefix to a route reflector, the route reflector will reflect that route to clients but not to other non-clients. Okay? And the third and final rule, eBGP. When a learned prefix is learned via eBGP up to a route reflector, that route reflector, because it's eBGP, learned route, it will advertise that learned prefix to both clients and non-clients. But really the benefit of route reflectors is this, is it addresses the problems, the limitations of scalability when it comes to iBGP, because we do not need this full mesh of connections. Again, using that formula of n in brackets n minus 1 divided by 2, you could see just how with 10 routers, how you needed 45 connections. Imagine if you had more than 10 routers, it becomes unmanageable. So route reflectors addresses the limitation you get with iBGP when it comes to scalability and the need to have a full mesh network. Now, with route reflectors, you still might need a next hop self because it really depends on the architecture. But just to make you aware, you still might need a next hop self policy definition, a policy option defined within that router. So just be aware of that. But absolutely, route reflectors gets rid of that problem, that limitation when it comes to iBGP and the amount of adjacencies you actually need. And here's the lab, and it's the same lab I've used for quite a few videos now that I've done on BGP. But if you haven't seen them, here's a quick overview as to what is configured and what you're actually seeing. So over here on the right hand side, we've got Enterprise B. And in Enterprise B ASN 65200, there are 4 routers. We've got R18, R20, R21, and down here R19. Now basically what each router is configured to do is to create a static route. For example, on R18, that is 18.18.18.18/32, and to then inject that into BGP. So the /32 is simulating that of a host's IP address. Likewise, on R19, you've then got 19.19.19.19/32. And likewise for R20, there's a 20/32. And for R21, there's a 21.21.21.21/32 as well. So basically, there's 4 static routes which are being imported, or exported, I should say, into BGP to simulate that of networks connected to these routers. What's happening at this point is all of these networks, the 18/32, the 19/32, the 20/32, the 21/32, they're being advertised out of Enterprise B into the service provider network. So that's for all 4 of those routers, all 4 of those /32s. And at this point, they're then coming into Enterprise A, ASN 65100, where these routers here, R5 and R10, are then advertising those learned prefixes across these connections to these route reflectors. There's the big point there, route reflectors. So this is what we're actually going to focus in on, of course, on this video, on this lab right now. And so I've just zoomed in a little bit into this cluster here. So just to recap, as these prefixes come in from the service providers through those routers R5 and R10, I think it was, this route reflector is then going to reflect those routes. And I just want to give a little bit more detail into the difference between client and non-clients. Now the key word on a BGP speaking router in Junos, if you want to configure a route reflector, is quite literally this: cluster. Is we define a cluster, and like an IPv4 address, it's 32 bits long. It has 4 octets. So here you can actually see I've defined a cluster 6.6.6.6. So this route reflector here, and it's not configured yet, is going to have a cluster ID of 6.6.6.6 because it's router R6. Of course, it makes sense. And so all of these neighbors, all of these iBGP peers, which are configured in that same group, will be clients. But this router here and the other 2 routers in Enterprise A, they're going to exist in a different group. So this router here, R5, this is a non-client because the group here is going to have a cluster command as shown here. Whereas this group, just call it group B, for example, that's not going to have a cluster command. So these routers are not going to know of a route reflector. It's not going to know that actually R6 over here is a route reflector. But as I said, the key word when it comes to configuring route reflectors in Junos is the cluster command. You configure this within a group, and within that group you're going to have neighbors configured as well. And however many neighbors you've got within that group, they will become clients. And the route reflector will then, as these routes come in to the route reflector, it will then reflect those routes onto this router here, onto this router here, and onto this router here. Likewise, if, just say for example, this router here has a prefix being learned, static or some kind of IGP, whatever it may be, and you redistribute that into iBGP, that's going to be advertised down to the route reflector, and then the route reflector will advertise that to other clients and also to non-clients as well. So it's only when you have non-clients advertising a prefix that the route reflector will not advertise that to other non-clients. But let's actually show you how quick and easy it is to configure a route reflector on Junos. So I've just started the secure CRT, the SSH connection into 2 routers, specifically into router R6, which is the route reflector, and onto router R7 here, which is going to be a client. Now, in terms of connectivity, everything is configured. The OSPF is configured. I haven't checked anything yet, so we may do a bit of troubleshooting, but that's always good. But obviously the purpose is to show you from R7's point of view how to build that connection to the route reflector and what do we need to do on the route reflector R6 to configure it to be a route reflector. As we know, that is the cluster command. So logging on to router R7 as highlighted, let's go into the CLI and let's go into, actually let's just do quickly a show OSPF neighbor. Let's see if we've built the adjacency. So we can actually see here it's built the full OSPF adjacency, that's what we want, to the out the GIGI 006 interface to the IP address of 192.168.10.33. That is the GIGI 007 interface on the route reflector. If you don't know OSPF, just check out this playlist. Done loads of videos on OSPF. But we got the OSPF running. Do we have iBGP or BGP running? So if I do show BGP summary, you can see BGP is not running. So we need to change that. So if I go into configure mode, and let's do edit protocols BGP, do show there's absolutely nothing configured there. Now what we need to do is we need to define a group. So I'm going to call this internal 65101. These clusters, just for your information, cluster 6666 and cluster 11.11.11.11 are in different ASNs. That's for a future video where we start talking about confederations. So even though Enterprise A has a autonomous system number of 65100, each of these clusters have their own autonomous system. So just don't get confused about that. But just in case if you are wondering why I'm entering in a different ASN to what's shown, that's why. It's for a later video where I'm going to talk about confederations. But here is the group internal iBGP 65101, and now I need to define the type. So if I define type internal, that means iBGP. I can also give my local autonomous system number 65101, and now I define a neighbor. So the neighbor is not the IP address on the interface, on the adjacent interface. It's actually the loopback address that's on router R6. So I just know that's 200.10.100.6. And now if I do show on that, you can actually see it's looking pretty good so far. So we've got our group name, type internal, local autonomous system, neighbor, and there's one thing I did forget, and that is the local address. So I need to define set group internal local address, and that's going to be using my loopback command IP address of 200.10.100.7. I had to check there, but if I just do a quick top show interfaces loopback 0, let's make sure it's correct. You can see I'm referencing the loopback address here, and it's configured here under loopback 0. And if I just do a run show route, have we learned the neighbors R6's loopback address via OSPF? So if I do run show route, you can see we've got it here. So here's 200.10.100.6 via OSPF out of the GigE 006 interface. So that's everything looking good. So if I do a quick commit check, and that's passed. And now if I commit to that configuration, and let's now move on to router R6, the route reflector as highlighted. So let's go into the command line interface, into configure mode, edit protocols BGP, and let's do a quick show. You can see there's quite a bit already configured here. Now here is the group internal AS 65100. So that's basically, if I move secure CRT out the way, that is the connection to router R5, R10, and across to R11 as well, I think. Let me get my secure CRT back up. So no, it's only going to router R10 and R5. It's not defined, but it doesn't matter. So these will be, R5 and R10 will be non-clients when I configure that cluster command. But note I've also got group route reflector 66666. Okay, so it's recommended that you use the router ID to be that of the cluster ID. So if I do top show routing options, you can actually see the route ID is configured to be 66666, which is why on the lab I've just done the diagram to show the cluster 6666, and that's why we're going to configure that on the Junos itself. It's just a recommendation, but it's highly advisable because it will stop any confusion actually from happening. Let's do a quick show again. So what we have here is our group route reflector 6666. It's type internal iBGP. I'm using my local address, that is the loopback address 200.10.100.6. My local autonomous system is 65101, and I want to peer to neighbors 200.10.100.8, which is router R8, neighbor 200.10.100.9, which is router R9, but you can see here that there's no IP address for router R7, so we need to change that. Let's edit the group route reflector and set the neighbor 200.10.100.7, and if I just do a quick run show route 200.10.100.7, see if it's in there, you can see it's inside the routing table. Actually now I can get to it via OSPF as well, via BGP, which is great. And if I just do a quick show again, you can now see I've got this configured here. So all three neighbors, R7, R8 and R9, are configured within this group, this cluster. Now the key word there, I keep saying it, is cluster. That's all you need to configure a Junos router, a Junos multi-layer switch to be a route reflector. So all we do is set cluster, hit question mark, and you enter in the cluster ID. So for here, I'm going to do 6666. Let's do a show, and there we go there. That's all you need to do on the route reflector. Let's just do a quick commit check. And that's succeeded, and I'm just going to commit and quit. And with that now committed, I'm going to do a show BGP summary just to see, do we have adjacency built to router R7? You're going to see quite a few adjacencies, but you can see here 200.10.100.7 is still actively trying. So let's give it a few seconds. Sometimes BGP can take a while. And there we go there. As I said, it just took a few seconds, but now it's established. It's been up for 12 seconds, and you can already see we've got packets coming in, we've got packets going out. That's great. That's all you need to do to configure Route Reflector to be a cluster. But has R7 learned of all these routes that are on the Route Reflectors or R6's routing table? So you can see we've got the 18/32. We've got the 19/32. We've got the, if I scroll back up, the 20/32, the 21/32. That is all those routers, those /32s, that's in Enterprise B's network. That is way across the network here. And if I just zoom out, that is from this route reflector here, it has connectivity, or it has visibility to get to Enterprise B via these two different ways, or even that way if it wanted to. So it has those routes, those prefixes in its routing table. But does router R7 learn or know of these prefixes? That's the question. And going back to router R7, let me just quit here and come out of the configuration mode. And let's just do a show route, spell it correctly. And now you can see we've got a few static routes here, but we've got the 18/32, the 19/32, the 20/32, the 21/32. So all of those routes, which have been learned by the route reflector via ISP1, and you can't see it, but via ISP2 as well, it's been automatically reflected onto router R7. But also note here, we can see BGP 170. We can see the autonomous system path that it actually comes from. We can see it's unverified right now, which is fine. So that's probably because I need a next hop self on the route reflector. Here's the curious thing for me right now, and I think this is a bit of a bug in Junos, is here we shouldn't be seeing 200.10.100.6. Let me just change that color to be something a bit brighter. So let me do that again. So this here, 200.10.100.6, that should actually be 6.6.6.6, i.e. the route reflectors, the cluster ID. So I think it's a bit of a bug in the VMX right now. It's free software, so you can't argue. But in a production network, you'd expect to see that cluster ID there instead of that loopback address of router R6. But nonetheless, route reflector is working. How do I know that? Well, if I just do show configuration, protocols BGP, you can see here I've only got the one neighbor command, which is to the neighbor 200.10.100.6. There's no neighbor commands for router R5, which is this router here. There's no neighbor commands for router R10, I think it is, which is this neighbor down here. There's no neighbor commands for this route reflector over here, which is router R11. No, there's only this one neighbor command, and that has allowed R7 to build that iBGP connection to the route reflector. And because that route reflector has that cluster command, it will then reflect all learned routes from itself onto the clients R7, R8 and R9. Well, that's it. That is route reflectors in a nutshell there. And so that's it, everybody. That is BGP route reflectors. In a short period of time, we've gone through what is a route reflector, what are the benefits of it, and the rule set plus how to configure it. But just as a quick summary, what is a route reflector? As the name says, it reflects routes. It reflects prefixes that it's learned from clients and non-clients and from eBGP peers to other clients and maybe to other non-clients, depending on where that prefix came from. And also the benefits, really, it significantly reduces that full mesh connectivity that you absolutely need with iBGP. And iBGP requires that because of the AS path, because it's a loop prevention mechanism. So Route Reflectors gets around that by reflecting routes and by not requiring a full mesh connectivity. So it significantly improves scalability within your network itself. And don't forget the rule set. Clients or neighbors which are defined within that group can, through the route reflector, can send and receive prefixes, again through the route reflector, or I should say the route reflector can advertise prefixes from one client to another client, and it can advertise prefixes from a non-client to a client, but it will not advertise prefixes from a non-client to another non-client. And just as we saw with eBGP, nothing really changes there. If it's an eBGP learned prefix, that route reflector will advertise that prefix to both clients and non-clients. And finally, how to configure this in Junos. All you need to do in Junos on the route reflector itself is, of course, define your local autonomous system, your local address, who your neighbors are. Those will be your clients, but the important one that you need to take away is the cluster command. Cluster 6666 or whatever it may be. It's a 32-bit 4-octet value. That's all you need. Again, recommendation is to have that to be the same of the router ID to keep things simple. What do you need to configure on those clients? Absolutely nothing. All you need to do is configure the neighbor IP address, the loopback address of that route reflector. And then iBGP will just do its thing, hopefully build the adjacency into that established state. So a lot of information, but that is the basics on BGP Route Reflectors. As always, I hope you found that useful, hope you found that informative. If you liked this video, please give me a thumbs up. Any questions or comments, let me know down in the comments box. I really enjoy hearing from you guys and hearing the questions you may have. And alternatively, if you wish to subscribe, please feel free to do so. Other than that, thanks for watching and goodbye.